Está 5 minutos atrasado? Então, posso falar em português? You know, you go to France sometimes. There's some French mathematicians. I'm not going to mention any names, but you know, you can guess who I'm talking about. Who insist on speaking in French, right? So, but I go talk. No, I'm not going to talk in Portuguese. Yeah. Okay. Oh. Okay. So we're going to talk about descent obstructions. And function fields. Let's set up is also k. So let me see. Little k is going to be a field. Later on I'll be more specific. And capital K over K is a function field and one variable over little k. So it has places. So you talk about the places of capital K that are trivial and little k, and there is a collection of places, and then they satisfy the product formula. So you can talk about local, global stuff, and so pretty much like we've been seeing a lot of talks about local, global structures in the number field case. We're going to look at some of these things in the function field case. I'm going to start with. So I want before even I start talking about varieties, let me mention an old fact of the term. I don't know. It's you know, I like to think of this term as basically Riemann-Roch. You can think of it as you know, a version of sad duality theorem, but the theorem is that. So, of course, you can talk about Adele. So here's A, K is Adele's of K. And the theorem is that if you have an Adele, then so that's V. So omega is a set of places, maybe. Omega is a set of places. This Adele is an element of K if and only if for all differential forms omega of K, so elements of the modulo differentials of K over K, the residue, sum of residues is 0. So this is just Riemann-Roch sad duality. Okay, so this is a local global principle for distinguishing one and Adele is global. And I want to turn this criterion into an obstruction for existence of integral points or whatever. So here's the theorem that, so this is a classical theorem, but, or maybe before I state this theorem, maybe I'll make some definitions. So let's let G be a group, I don't know, group scheme over K. Okay, something, I don't know. X a variety, and a map pi y to x, a G torsor. So I'm just going to talk about descent obstructions, which is, you know, we've seen people talk about descent obstructions for tori. There was some mention of finite descent obstructions. I just want to, you know, you have to put some extra hypothesis, but certainly you can, if you have a G torsor, then the fibers of this map are G torsors. And so over K, so you have a map from rational points, K rational points of X to the set that classifies G torsors over K. So this is the first cohomology set. If the group is non-abelian, if the group is abelian, it's a cohomology group that maps a point to the fiber, the class of the fiber, right? And so there's an obstruction, so you can look at adelic points. I don't know, maybe I could call it pi. The set of adelic points obstructed by the torsor pi is the set of points PV in, I don't know, such that the class, so the class of, well, right, pi inverse of PV actually belongs to H1kg. So if you start with an arbitrary adel, so these are going to be elements in XKV, then the class of the torsor is in H1KVG. But you can ask, if you have an adelic point, whether the collection of local torsors actually come from a global torsor. And that's the set of points, adelic points obstructed by the cover, pi, the torsor. Yes? I don't want to be precise, you know. If you press me too hard, maybe I'll restrict to etal or whatever, but. Okay, so in the case that the group is abelian, this is related with Brownian obstructions, the finite abelian groups, that you can relate this obstruction to Brownian obstructions. Maybe I'll say a few things about this later, but that's not the point of view that I want to take is the point of view of the descent obstructions. So here's a theorem I want to start with. Joint work with the Harari. Is that if little k is a finite field, so little k is the field of constants of my function field, so I'm taking little k to be a finite field, so capital K is a global function field in one variable is over a finite field, so then, and x over capital K is an affine variety. So no hypothesis, you know, can be as singular as you like, can be as complicated as you like, it's just an affine variety, there's no geometry. Then how am I say this? You know, the points, the integral adelic points unobstructed by all covers of the form so look at a regular function on X, and you take a cover, an arbitrary type cover, y q minus 1. Q is not the cardinality of little k, okay? Q is just some power of the characteristic. Of characteristic of k are the integral points. So maybe I should be precise what I. If you look at So for any, for any set, finite set S in omega finite, the intersection over pi of this form, so these are covers like that, right? So when the group scheme is G is yq minus y equals 0. This is a finite field. Intersection over all pi's like that of maybe product of V not in S. I should be taking an integral model for X, but maybe I'm not going to write it. KV. So you take the intersection of all the things that are obstructed in that sense. This is just a set of integral points. So it's a surprising theorem because, for a number of fields, we've been hearing many talks about trying to prove that certain varieties satisfy Hasse principle, or the Brahmanian obstruction is the only obstruction to weak approximation, or to the Hasse principle, or whatever. And here, is an example where a situation in every affine variety, you have, in fact, so this thing here is, I don't know what I'm going to do. X is adelic points. The S integral adelic points, and this is actually one thing that you can prove. So this, I guess, these two equalities are both theorems that need to be proved. In fact, is the things orthogonal to the P torsion in the Brouwer group. So not only you can do Brahmanian obstructions, the only obstruction to stronger approximation or whatever, but you can only need the P torsion in the Brouwer group. Of course, this is true because the P torsion in the Brouwer group of X, P. The P torsion of the Brouwer group of an affine variety characteristic P is enormous. Right, so that's what's behind this theorem, if you want to look at it from the point of view of. And that theorem is basically this. So let me sort of sketch how come that, you can, so in fact, you can take X to be A1. I mean, the A1 is, is a central case. You can do A1, you can do all varieties just by projecting to the various coordinates. You can, so if you take a cover of A1 given by something like little f, so that's A1 with coordinate x. So you take covers of A1 of this type, just a function type, so f is an element of K. So I don't need all the regular functions in the function field. There's regular functions that have multiples of the constant multiples of this constant, not constant in the sense of little k, constant in the sense of big K. So looking at those covers, so yes, so what is H1 K? Well, maybe this is q minus y equals 0. Is K modulo, I don't know, alpha q minus alpha and K. So this is a description of the cohomology group that comes out of the, you have the, I mean, if I define this function P of X, P of alpha to be alpha q minus alpha, then you have 0 yq minus y equals 0, goes to k bar, goes by p to 0. And you take cohomology of that, you get this. So what does it mean for a torsor to be, an adelic point to be unobstructed by this torsor. By this cover, it means that, so a point on a del xv is unobstructed. And a del is just a point in here, right? So if and only if there exists some yv in kv, I don't know, such that yv to the q and well, is unobstructed, it means that there is some global class, some twist of this of this cover by a global class so let me just write it as fxv plus a. So a is the element in this group that represents the global class, and is something like that. And then you have to be a little careful about where the poles of this guy lie. That's why I have to state it in terms of integral points and not just rational points. You want these guys to be integral in the same place that the xv's are integral. And you can use an old result of Cartier that says that the residue of where t is a local parameter or something, or a separating variable of the field. So you get, so this is always true. That's just because the way things are set up. So you get that the fxv f dt over t, the residue is minus the residue at v of a dt over t. But now, the differential on the right-hand side there is global. So when you sum the residues, you get 0, right? So you get, this equality is true place by place, and then you can just sum, and then this is 0. So, and every differential form on k can be represented in this, so you apply this theorem and you get the thing on the other end. So this theorem is, I don't know, it's surprising, but the proof is easy. So it's even more surprising because, it sounds like, Of course, I asked Cyril a question in his talk about État-Bras obstructions on linear algebraic groups, and he mentioned that, it's true, but it's not very useful because there are too many elements in a Bras group, too many, you can't prove any finiteness. It's the same situation here. So this result is surprising, but it's not very useful because the Bras group is so big. You can turn it into a criterion for deciding whether a variety has an integral point or not. Not automatically. I mean, sometimes you can use it to prove that things have no points and so on, but. Anyway. But so this is for affine varieties, and that's I wanted to say something about projective varieties. And so that gives me an excuse to explain a very interesting construction, which I think is due to Bouillon, of the first Z space of a variety. So let me. So this is first jet space of a variety x. So let's start with x over k as before. I want to write, well, I can always choose, I already chosen, I guess, but I didn't write it down, but let me write it k over kt. So choose t. This is finite separable. So this is separating variable. So write your function field as a finite extension of the rational function field. So you have a derivation, which I'm going to call delta, just ddt. It's a derivation on k. So if x is an affine, is a zero set, so we're just going to write it as f1, f2, fk equals 0, or not k, fm equals 0, where fi is, let's say, polynomials x1, xn. I want to define, so this is an affine variety defined by the common vanishing of a set of polynomials. I want to define a variety x1. So this is inside AM, I guess, m-dimensional affine space. I want to define x1, which is going to be a variety inside of A2M, which has coordinates x1, xn, x1, xm, y1, ym, n. Okay. x1, xn, y1. So n is the dimension of the ambient space, m is the number of equations. Okay, so I want to write this variety x1 in terms of give you a system of equations. So is fi equals 0, and also the equation sum of gfi dxj yj plus f delta equals 0. Okay? So this is a variety. So let me explain what f delta is. I'm not going to write it down. F delta is just take your polynomial, or fi delta. So this is a polynomial coefficients in capital K. Just differentiate the coefficients. So you get a new polynomial whose coefficients of the new polynomial are just the derivatives of the coefficients of the old polynomial. So that's what this guy is. This is the usual partial derivative with respect to the variables. And so this variety is, well, because it's defined by those equations that contain those, it projects, so x1 maps to x, right? If you project on the first n coordinates, you're just looking at these. So x1 maps to x, and the phi bar is an affine variety. It's a linear, affine in the sense of linear. So it's a torsor for the tangent bundle, if you want. Okay? And so this is a definition of x1 for affine. If if x is arbitrary, define f1, define x1. So arbitrary being, quasi-projective, I guess, by covering by affines, I don't know, UI, and gluing the UI1. So this is a construction that you can make for an arbitrary variety or projective variety if you want. You cover it by affine patches. You have the description of x1 there for each affine patch, and then they naturally glue with the same way that UI is glued, and you get the. So I gave this talk, similar talk about a month ago at Berkeley, and Arthur Rogus asked me, "What's the functor of points?" Classically trained, Grothendieck style algebraic geometry. I just said, I don't know, you figure it out. Anyway. Huh? Did he figure it out? I guess, I don't know. I'm sure he can. Anyway, so one important thing about this variety is that there is a map, which I'm going to call nabla, from xk. So it's not an algebraic map. It's called a differential algebraic map. Is a map that is given in terms of the coordinates and their derivatives, which on affine patches sends a point. If you have a point with coordinates, say 1an, say so in this setting here of affine varieties, and you just map it to, well, so I have to give 2n coordinates, right? The a1ans, because it has to project back to x, and their derivatives. So, of course, those equations here are just produced for this map to land in there. I mean, this is just a chain rule. The chain rule So if you take the, since I'm taking a point here, you have f of a1, fj of a1 an equals 0. If you differentiate this with respect to t and use the chain rule, you get those equations there. So is this, and of course, nabla is a section of this map, the set theoretic sense, right? So if you lift and project. And here's a very nice theorem, is that if x over k is a smooth projective curve of genus g greater or equal to 2 with non-zero Kodaira-Spencer class, so I'm not going to define precisely what the Kodaira-Spencer class means, but it's something that measures the variation. So you look at this. If you have a curve over a function field, then it means it's a family of curves over the curve whose function field, the function field in one variable is the function field of some curve. So you have a family of curves over this base, and the Kodaira-Spencer class is the derivative of the variation of this thing. So it's a derivative of moduli. So non-zero Kodaira-Spencer class, it's stronger than varying moduli because we can be in characteristic P, and in characteristic P, having non-zero derivative is stronger than being non-constant. Okay, then x1, this variety that I construct here, is affine. So you start with a projective curve, and you can manufacture an affine curve, an affine surface related to this curve, together with this map that moves points here to points there. So you can apply this, and you get a description. So it's even better than, so in the context of global fields, the rational points here get mapped to integral points for S integral points for some S in here. So you're actually even better than rational points. You land in the poles, the places where these points are not integral. It's very controlled. And so you can use this to describe the set of rational points on X by actually a finite number. So if you do this right, because of projectivity, you can use the projectivity to advantage, and you get a finite number of things. Well, maybe the Q, finite number of covers like that, except not Fi. Fi are regular functions on X1. You have to compose with this map nabla. So this is what's called, maybe it's a cover in the category of differential algebraic variety. So it's not a cover in the category of algebraic varieties, so it's not you sort of escaped the realm of usual algebraic geometry. You have to look not just at algebraic equations, but at differential equations. Okay, so that's very nice. So this maybe, I don't know, corollary, xk. So x as in here, xk can be described by finitely many differential descent obstructions. If little k is finite. And because I'm combining Boolean's theorem, which is a purely geometric theorem, if you like, with the term that I proved the hierarchy over there. And you get this. So an interesting question is, what can you do in higher dimensions? So this is for curves. Even, not all for all curves, you have conditional non-zero Kodaira-Spencer class. If you remove that, then, it's no longer true that x1 will be affine. But it's still true that for curves, for any curve, x1 has lots of regular functions. So you can use these regular functions. So even though they don't embed in affine space, you still have regular functions that you can use to try and get descent obstructions, and it's not clear what you get. I mean, I think if I was playing around with the sort of diametrically opposite case of constant curves. So if you have a curve that is actually defined over the field little k, then I think you can detect rational points, capital K rational points, which are not little k rational points with the descent obstructions. But the descent obstructions don't see the little k rational points. And you can make adelic points. You can take an adelic point. All of those coordinates come from little k, but they are different for each place. So you can get lots of funny adelic points, and those obstructions do not see them. So in the sort of complementary case of constant curves, you get something funny. I don't know what's happening in the middle. Be interesting to look at this, and be interesting to look at the case of elliptic curves, which is also a situation where even if the Kodaira-Spencer class is not zero, x1 is not affine, but does have regular functions. So you could look at the case of elliptic curves and see what you get. And higher dimensional varieties, again, there's all sorts of possibilities. I don't know. Okay, so this is what I wanted to say in characteristic P. I want to also talk a little bit about characteristic 0. Unfortunately, not number fields. I don't know what, I'd love to be able to generalize some of these ideas to number fields, but where is Oliver? I need F1. Where is he gone? And I need F1. That's what we all need, right? But okay, so you tell him that he should hurry up. Yeah, he can see it. Yeah. F1. I need F1. Okay, so let's take little k to be, I don't know, a favorite field of characteristic 0. So capital K is still a function field of one variable over there. I want to write down, so I want to talk about this idea of having this differential descent obstructions where you allow equations, not just algebraic equations, but differential equations. And, it's still here. So here I use the field of constants, right? So this defines this equation defines FQ, right? This is FQ. So I want to capture the constant. So if I am so this is a subgroup of the additive group, right? GA. Here I wanted to capture the constants here, and one way to capture the constants that we teach our calculus students, those of us who teach calculus students, by the constants are things that have derivative 0, right? So here's an equation that delta y equals 0. If you like, it's a subgroup of the additive group, right? The constants form a subgroup of the additive group, and derivative equals 0 is a linear equation for the constants. So we could look at, so we could sort of, so if you have an affine variety, so maybe, okay, so K over K is a function field, X over capital K affine variety. If capital F is some regular function on X, we can look at this differential equation and think of it as a cover. So this defines some object in the category of differential algebraic varieties. So it's an y. Y maps to x, right? Because, this is a function on x, so we just y maps to x, and by ignoring the little y. And the fibers are torsors for this guy. So you have a well, I guess you can, well, there is a way of doing cohomology that gives a cohomological interpretation to these things and computes the H1 in the appropriate sense to get the classification of the torsors. But if you want to just be formal, I could define this like this. So just take the elements of K modulo the derivatives is a group, right? So and this sort of classifies torsors for this group here, and so you have, so what so you have a map from xk to that sends a point P. So I'm just defining this formula, right? So I have this affine variety. I have the rational point. I have a regular function. I can compute this regular function and the point, and view it in this quotient group. So this is the class of the fiber here, just formally, but yeah. And you can ask, if you have an adelic point, you can ask the question which adelic points are unobstructed by all the torsors. So I have to remove David's name from here. He's not, I don't mean any offense. I mean, a lot of the ideas that come to this work was inspired by collaboration with him, but this is something I've done more recently. So if K is equal to C, well, K is a field of characteristic 0. That's an affine variety. Then the integral adelic points obstructed by all the covers, all differential covers in that sense. So I'm taking things in that sense. I don't have a broad group interpretation, unfortunately. I'm erasing it because I don't want to make false claims. I'd love to have a interpretation of this beast here in terms of broad groups. So question, but that's the theorem. The theorem, and the proof is the same. The proof is. So now you have something like delta yv. So if something is unobstructed, you're going to have something like that. And this here is even easier because a derivative has no residue. So when you take residues here, the residue disappear, and then you do the same trick. The sum of the residues of a global thing is 0. So you get the sum of the residues of something like that is going to be 0, and you get the thing is global. So the proof of that theorem there is essentially the same proof as the other theorem, but it's even easier. And you can apply, again, the same thing you can do, right? So now, we've already differentiating there. You can keep on differentiating again. So the corollary is that, I don't know, xk, if x is a curve, just like here, xk is described by finitely many obstructions. I don't know, delta y equals fi. All composed with nabla and fi, regular functions on x1. Yeah, so again, it's the same thing as before. You have to pass from the curve x to the affine surface x1, and you have obstructions. Okay, the big question here, one question here is, does this have an interpretation as some kind of Brownian obstruction? No, I started late, but I'm going to finish early. Yeah, that's pretty much all I wanted to say. Thank you.